Alright, it's about time. Let's get started. So today's class will be recorded by David. It's required by the department, and except that, nothing special. And I'm wearing better, as you can tell. Week 7. Today, some of the announcements. Our project is due December 6th. It's still, a month, like half a month away now. And there will be no discussion next week because it's Thanksgiving. And then I'm subbing for another TA this week. So the week that's after Thanksgiving, that discussion might be subbed back from the other TA, which is sunbaking. Today's goal, I'm going to talk about Dhcp, which is a protocol that's how you dynamically get your IP address. And then there's this thing called NAT that's so important that you have to know this. I think George talked a little bit about NAT, but I'm going to go into detail about NAT. And then I'm going to talk about the layer 2 to 3 overview. That'll hopefully help you guys a lot with the project, the skeleton of the project. And then I'm going to talk about fragmentation. I'm pretty sure one of the final exam question will be one of these fragmentation. And then finally, I'm going to go into the link state. I'm just going to talk about how link state algorithm, our protocol, works based on Dijkstra's algorithm. Any questions before I get started, or any particular topic you'd like to know? All right, cool. So let me first talk about Dhcp. This is a protocol. Again, this protocol is used in layer 3. We spent 4 weeks in the physical layer. Then we went to data link layer where we did bridge, hubs, and all the Ethernet, all the MAC address. Remember, that's the second layer. And then we go to the third layer. This third layer is networks layer, and then the protocol of Dhcp is mostly used over here. That's where you get IP. The third layer connects LANs together. Remember LANs like local area networks. And then, to be able to forward a packet from one LAN to the other LAN, you need to use IP, right? So the IP, how do you get IP? That's how you talk to different LANs. So here's this protocol called Dhcp, Dynamic Host Configuration Protocol. So basically, if you have a new device connecting to a local area network, what do you already have when you have a device? What kind of address do you have when you have it? MAC address? That's good. So if you have a new device, it comes with a MAC address. That's like a physically, it comes with an address. It's a unique address that comes with the device. And once they connect to one of the networks, which is local area network, it requires an IP address. So this IP address is for you to talk to to get into the internet. So to do that, we need to use the Dhcp. So there's a server called Dhcp server. It holds a bunch of IP address. And when you first join that network, you're going to ask the server to assign you a IP address. So the way to do that is that it's very similar to Bridge, that when you first get into the internet, you're going to ask the Dhcp server saying that, hey, I don't know who owns a bunch of IP, so I'm new to the internet, so can I get an IP address? Then the Dhcp is going to reply, also broadcast because it doesn't know where you are. It's going to give you a list of IP address. So remember, this is Dhcp, this is server. And then it's already connecting to a bunch of hosts, host 1, host 2, and then you want to join this, so that's you, right? So you broadcast into this network, and then it's going to give you a list of IP, and then you're going to choose one of the IP address. So basically you're talking by broadcasting, because you don't know where the Dhcp is. So the Dhcp is saying, okay, you can pick any of the address over here, and then once you picked one of the addresses, you're saying, hey, I'll take this address. Say 128 point star point star point star. All right. Those are just starts, just some fake IP. And then DHCP is going to send an acknowledgement back to you saying that, okay, you got the IP address. That's how you get the IP address when you join a network. Once you have this IP address, you're officially connected to the internet, and then you can talk to the other LANs and other networks that's separated by the router. So, quick question, how do you talk internally? We talked about that last week. How do you talk to other devices? Or which layer are you working on when you talk to other devices within the LAN? Data link, yeah. So when you try to go outside the LAN, you're talking to layer 3. The way we talk in the data link layer, we use MAC address. We use hardware devices like bridges and hubs. And then if you're going to layer 3, you're mostly using router. So that's a big difference. Those are just a hardware difference. All right, any questions about DHCP? You need to get, yeah.
So the only thing DHCP does is to give us an IP address?
Yes.
Okay.
Dynamically give you IP address.
Okay, so it's not used in anything else?
Yeah, nothing else.
Okay.
But that's a huge particle. That's already huge. So keep in mind that this IP is not permanent because it's dynamically assigned, so it could change if you leave the server. This IP address is available again. If some other device join the server or join the network, it's probably going to assign this IP address to someone else. So within a network, your IP address may change. That's why it's called dynamic. Yeah.
I think Professor mentioned in lecture about how like IP addresses could expire or like have a timeout. Does DHCP also handle that?
Yes, it does. Because as you mentioned, the IP could expire. Why do we do that is because we want to monitor if the device is still connected to the network. There's no other way to monitor that. So assume that H1, my host 1 left this server. So the IP address is going to time out. So that IP address will be available again. So for any other user that joined the network, then it's going to use the old IP address. It's like you're holding your phone, walking around UCLA campus, and if you're walking too far away, you get disconnected, right? That's the idea of getting IP address. So, yeah.
You said that if we want to talk to data LAN, it's only about the data link layer, right? So I'm new to the LAN. How could I know others' MAC address?
You don't know the MAC address, and yeah, when you join the LAN, you can broadcast. So initially, remember how the bridge works? You join the network, you don't know the MAC address for other people, and then you go to the bridge, you send the packet to the bridge, and the bridge will broadcast your message to everyone else, and you're going to learn MAC address. You're going to get the MAC address from the bridge. One of the homework problems saying that you have an intro server. That's probably one of the protocols that you can use, and then the intro server is going to tell you the MAC address from other hosts. All right. Any other questions about that? Okay. So then let's talk about NAT. This is network address translation. Remember we have IPv4. It supports only 2 to the 32 roughly 2 to the 32 number of hosts. So that's very limited. What this protocol does is that you can share. So a group of devices can share one IP address. So for example, if I have H1, H2, and you connecting to a router over here. So the DHCP server can be in the router. So if you have a router and it's connecting to some other network outside, so the router is going to have an IP, say 128.100.0.6. I just made it up. What NAT is doing is that, okay, if you're within this local area network, you guys are sharing this public IP, and within the network, you're going to have your own IP. Remember, I talked about some of the IP addresses that are reserved. For example, endpoint star, point star, point star. those are reserved, those are private networks address. And then also 192.168.*. Those are reserved IP addresses. These IP addresses come into play because once you share this public IP address, for the outside world, you guys all have this address. And then inside, to distinguish the host, you're going to use these reserved IP addresses. These addresses are not public. So if you do 128.100.0.6, and then that will get you to here. And then the router is gonna tell that you own, because it gives you a dynamic DHCP, gives you new addresses. You're gonna have different reserved address. So you say this one's 10.0.0.8. This is 10.0.0.9. Then what this NAT is doing is that it translates your host to a reserved IP address, and then some other host, your different address. So you guys can share one public IP while maintain a personal IP, which is only works inside the local area network. So that's the main idea of the NAT translation. What does it look like? It looks like 10 point star or 192.168 point star. And I think there's another reserved IP address. I don't remember it on top of my head. So a quick question: how many hosts can these reserved IP addresses support? So if you have 3 stars, if you're using the prefix with 10, how many hosts can you support within the local area network? 2 to the 24. Right. Because these 8 are the same, and you're going to have 2 to the 24 number of machines connecting to sharing one public IP address. That results in an issue of very limited IPv4. And so similarly, if you're using this prefix with the first 16 bits reserved, then you're going to be able to support 2 to the 16th machine. So why do we do this again? Is because we're using IPv4. V4 stands for 4 bytes. And then we're currently, the new networks technology, they're trying to use IPv6, which supports 2 to the 30, 6 bytes. And so that's a lot more machine to support. So how does it work? So this is your router, and this. All right. So this, we're using 10.0.0.1 to mark one of our inside machine. So we're saying that this local area network, you guys share the prefix starting from 10, and you guys have the public address of, let's see, public address of 138.76.29.7. So you guys share the same address over here. The first thing, if you want to send a packet to the outside world, you'll see that we added a new feature called port number. So basically it's saying that if you see this public address, that means I'm navigating to this point. And then the port number is indicating, okay, 5001, that points me to this machine. If you have 502, it's going to be 10.0.0.2. So adding this port number makes it easier to manage what's inside your local machine. So when you're sending a packet to the outside world, you see that it goes to this IP address and this port number. So they're using the NAT translation again. They're using the NAT translation as well. And once this packet gets to here, your local IP address will be changed to this public IP address, translated into 138.76.29.7, and then it goes outside. Remember that you're going outside with the port number 5001, so the other side will remember that this packet comes from this machine. All right, everyone with me so far? So when the other side receives something and reply with a message, it's going to say the destination is to 5001. What does that do when the packet gets here? what do when we see the 5001? We look at the table, and then 5001 is it's mapping to this machine. So this packet gets back, gets it here.
Right. One more time again, how did you get the source in step 2?
And step 2, how do you get the source?
Yeah.
So
Destination you already have.
initially, I have my IP address, my private IP address to be this. So there's in this router, I have a translation table
Okay.
that's saying that. Yeah, got it. All right, cool. So what does the 3345 do? You might wonder. Can anyone guess that? This is also a port number on your own machine.
Different applications?
Yes, exactly. So you to distinguish the applications. For example, 3345 is browser, and 8080 is some of your Angular applications, stuff like that. So to distinguish different application, you use different port number. All right. So we haven't talked about the application yet, but we're getting there. We're halfway through, more than halfway through. So that'll be more exciting. Then finally, the packet gets back to here, and now the NAT router changes the datagram destination address from the public address to the private address again. So that way, we're translating the network address so that we support more machine and without affecting the data packet translation. So, yeah.
How you make that table? I mean, is it stored in Bunche in every?
It's stored only in your local router because when you go out and in, you look up. You need a translation. You don't store the information from other router How do you get this table? They run different. When you join the network, it's going to set up a translation table. It's going to map your IP to a private IP. So it's likely to be done during the Dhcp protocol. I don't know the detail of that, but it's very likely to be done in the network.
So you should have information on any single node, yeah?
Yeah. It has a translation to every single node once you join the network. Also, so since we have time to live time period for the dynamic IP address, this entry is also limited. They have a timer on there. They expire too. So you constantly update the network table, the translation table. All right. Any questions so far? All right. So with that said, we know how to get IP address. We know how to get the MAC address last week. Now, this is basically what your project is going to ask you to do. So you want to send a packet from client to server, in which I mark them as PC1 and PC2. In between, there could be a lot of router, but in your project, there's only one router. There's only two different server. And so let's take a look at how this packet gets from PC1 to PC2. All right. So when you have a packet, initially you have an Ethernet header. A packet is going to look like this. So in the very core, in the very center, you're going to have the application, the information of the real application. If you send a hello, hello is going to store over here. And it's going to, if you go down a layer, so application layer maps to here, right? So, and then you have HTTP header, which is, it's kind of between the application and transport layer. And then you're going to attach the TCP, which is another protocol inside a transport layer. Then you go down one layer, you're going to attach the IP address on the side so that you know where the packet is forwarding to. So you want to go to, from source to destination, those information are stored inside this IP header. Then you're going to have the Ethernet header, which tells you the MAC address. So what is the next step? What is the next hop router? So you use the Ethernet header to travel within the network. So let's take a look at this. So Ethernet header source. So these they're gonna have their MAC address PC1, IP address PC1. They have different MAC address, different IP address. In this case, we're not translating any IP. So, what's the Ethernet header for the source? Remember, you're gonna have you're sending from PC1 to PC2. What information do I store in the IP or the Ethernet header source? Ethernet is in the second layer, so we use MAC PC1. Exactly. So what's going to be our destination? Ethernet header destination.
Like PC2?
MAC PC2 or
You don't know that.
you assume that we know all the MAC addresses so far. You want to get to PC2, that's right. But we're in layer 2. So you want to get to R1 because R1 is your first hop router. This is the router that connects all the local area networks, all the hosts in the LAN with the outside world. You want to throw this packet away by going to R1, and then you leave the rest of R1. R1 is going to deal with the packet because you're going to have the IP for source, which is PC1, destination is PC2. You don't care what happens next. You trust R1 is going to forward this packet. If not, R1 is going to give you a feedback saying that the packet is lost. So you want to set the Ethernet header destination to R1. So basically, this is what this red arrow is doing. And then what's the IP header source? Yeah, PC1. So what's going to be our IP header destination? PC2, exactly. So during this red arrow, we put our MAC1, our header with the source of PC1, and then the destination of R1 attach that inside our Ethernet header, and then once the packet gets to R1 checks the Ethernet header. It'll say, okay, you're from PC1, you're here, you're at the right place on R1. What is it? What does R1 do? Suppose that we found, that's a router. So router decides what is the best path to get to your destination. Suppose that the router has done what we've done on Thursday. It decides that, okay, going through R4 will be the best path. So R1's going to take a look at this Ethernet packet or attach the header. It's going to strip off the header and put a new header in. Modify the header so that it can get to R4. All right. Any questions so far? I want to make sure everyone understands that. So the packet gets to R1. R1 take a look at the Ethernet header, and it take a look at with the destination, what is the next destination is, and I'm going to modify the Ethernet header so this packet gets transmitted to R4. So what do we do? What do we put in the Ethernet header? So the source is going to be R1, the MAC address of R1, and the destination is going to be the MAC address of R4, with the same IP and from source to destination, right? So remember the IP tells you where exactly you're going, and this Ethernet header tells you what is the layer 2 operation is. So where are you going internally? So from R1 to R4, you check the routing table because once that's calculated in the networks layer. So let's assume that we know that R1 to R4 is the best way to go. And then now the table says R4 is the best next hop router. So reassemble the frame. So basically you strip off the Ethernet header and then replace with a new header saying that you're from R1 to R4 with the IP header still be the source and destination. So imagine there's more routers in between. You're going to keep changing the Ethernet header until you get to the PC2. So the PC2 will take a look at it'll take a look at Ethernet header, I am already PC2, so I'm strip out these network Ethernet header, and I'm going to take a look at this IP header. This is to me. So I'm going to strip out this IP header, and then I'm going to pass one layer up, so I'll let the TCP layer deal with the rest. And with all these operations done in a different layer, you'll eventually get the information, maybe hello, from your app. So what if I don't know the MAC address of PC2 in the step where I'm trying to forward a packet from R4 to PC2? What should I do if I don't know the MAC address? Use ARP, right? So to approach this type of question, you want to analyze where the issue is. So the MAC address, if I don't know MAC address, that's my layer 2, which is data link layer. So remember that we have an ARP protocol that maps the IP address to the MAC address. So we can kind of like broadcast into my local area network to ask the IP or MAC address of this PC2. Once we learn that using ARP, then we're able to reassemble the packet again and then forward it back to R2 or PC2. So I don't know this, I'm going to use ARP. Alright, so this is the detail about ARP. You're going to have ARP request, ARP reply, and ARP cache. So you ask for an ARP, and then you get a reply from someone with the MAC address, and then you're going to store the MAC address. So this is what we've been doing 2 weeks ago. This is what you're going to do in the project. If you don't know the MAC address, you ask for one. Once you get the ARP reply, then you store it in ARP cache. Any questions about this? All right. So basically that's what your project's going to do. You're going to take an Ethernet frame, and you're going to take a look at if that's a ARP or that's an IP, and then you do different tasks. So hopefully that'll help you guys a lot with the project. And the pseudocode is in Professor's lecture slides. You can just once you understand the material, the rest of the stuff is just translate the pseudocode from English to C++ and make that possible.
So the frame is on both ends of the frame?
I draw this diagram to, sometimes people do that, app or app, TCP, it doesn't have to be on both ends. This is just to visualize how the layering works. So this is you're attaching the header. Sometimes the header, they have like the header at the end. I don't know if there's a term for that. But for IP, they have only the first 20 bytes are the IP header. So in case that the content are stored, so in case the content of the application, say the hello world or hello is stored in between, you're gonna have some end header, some information from other layer at the bottom and the top, and that's how this structure will look like. So, but the important thing is that if different layer, they deal with different tasks. So, what does physical layer do? Again, we spent 4 weeks on this. To make sure that all the bits inside this file or the frame gets translated successfully, right? So we don't want to make many mistakes over here. And data link, this layer, what does that do? What's the job of data link layer? Sending the packet within the LAN successfully to the right target, right? And then the networks layer, similarly, you want to forward the packet from one host to the other host that's outside of your LAN. And then we're going to do some interesting stuff over here in the future. So each layer, they're doing different tasks to make sure that you get this packet. And this is the divide and conquer idea. You divide different tasks into different layer, and you solve this inside different layer. All right. So, any questions about the structure of ARP and how you get the packet from one host to the other host? Yes.
Just one question. Is the final destination is in the IP header, right?
The final destination, yes, it's in the IP header.
So every time a router receives this frame, it looks at the IP header, right?
Yes, it looks at the IP header. That's how you determine what in this which router you'll go next. So because you calculate the shortest path based on that. Yeah, that's right. All right. So IP fragmentation. We can't have too long of an IP datagram. We cannot have too short of an IP datagram. Why is that? So we talked about the minimum IP, the minimum packet size, which is not necessarily IP, it's in the Ethernet, but their reasoning are similar. So we had a homework problem on the minimum packet size. Why do we need to maintain a minimum packet size? Anyone still remember?
To detect collisions.
To detect collisions, exactly. If it's too small, then you can't detect collision between. But that's in the Ethernet. Similarly, you can't have too large of a datagram. Why? Overhead? Overhead? Not quite. Overhead happens in smaller datagram. Why can't you do a large IP frame?
Some routers have a max size.
Yeah, some routers restrict their size, so you cannot drive a 30 feet wide truck in the real world, right? Because their road's not that wide. Similar reason, the IP fragmentation. There's a standard for all the routers, so they accept standardized size IP frame. So if your frame is too big, we're gonna break it into different chunks, and then we're gonna send it. And then hopefully the next, when it gets to the destination, it's going to reassemble. So this is what IP fragmentation is. We have a term called max transfer size, which is MTU. That's the largest possible link level frame that you can translate, or you can transmit to the other router or to the other end. So. This is, I think this is optional material, but so I'm going to go over this pretty quickly. That's pretty important. So imagine that you have a 4,000 byte datagram, and the maximum so MTU is going to be 1,500 bytes. So you're going to break it into different chunks. However, for the IP, since we're dealing with the IP, the IP header is always going to be 20 bytes. The header, so you're going to have 20 bytes of the header in each fragment, and you're going to have the actual content. This 20 byte, it tells you the destination, tells you the source, it tells you the ID and offset. What are the so I'm going to explain this real quick. So basically it tells you the general information and some optional information about this fragment. And then, so this will be sent to the other side, and the other side will put these actual content together. It'll delete this 20 bytes and put, hopefully it'll put the puzzles back together, and it'll get the original IP frame. So the flag, this tells you that you have so this is not the end, it tells you that this is not the end of my fragmentation. So each fragment is supposed that you break this into 4,000 bytes into 3 different fragments. This is your first one. You know that you're saying this is one. That means that you have something that's behind and coming in, and that belongs to the original 4,000 bytes. And then the flag, when it says 0, that means this is my end of the this IP fragment. So that means I don't have anything that's after me, so you can go ahead and put these back together. And the offset just tells you that what position you should insert my actual content in. So initially we have 1480 bytes transmitted. So over here we stop at 1480, and the offset is 0. Then when you reassemble this datagram, you're gonna put the actual content from the offset of 0. So you get the actual content gets copied over here in a buffer. And then the second time, if you receive a datagram with an offset of 185, so you use this, multiply by 8, that's going to be your bit sequence. So you're going to basically start from a 1480, and you attach the second datagram over here. And you do the similar task for all the datagrams, and then offset tells you where to put those frames back together. So with everything over here, if you reassemble them, it's going to be the original one. So yeah.
Fragmentation is for content or
For the content.
header? For
Header is mandatory for all the IP, for all the packets. The header tells you the information about the content, but what you're really interested in is the actual content. So with that said, header is mandatory. So what would happen if, suppose that the MTU is 4,000 bytes, and you can send, the maximum size is 4,000, but you insist to send 1,500 bytes instead. What is the disadvantage for that?
When you have header for each fragment. Right?
Yeah, you're going to have the 20 byte mandatory header for each fragment. That's overhead. Right? So you don't want the header. So if you're sending, you can send 4,000 bytes. You can just send 4,000 bytes once and finish sending everything. Instead, you send, more dramatically 80 bytes per time. Then you're going to add this 20 byte header to the 80 bytes, and you're going to have to add 24 the rest of all of them. And then that's just too much header, and that's what we're getting for.
So is the length supposed to include the header size as well as the field size?
The length includes the header file size. Let me double check. Yeah. So the 20 bytes for the header, and the total length of this piece of datagram is 1,500. That's why you're going to have 1480 for actual content.
Shouldn't be the third length be 1060 then?
1060.
Because
Yes, you're right. Yeah, it should be 1060. But so all you need to know is that you have to have a header for all your datagram. That header could be overhead. You have to pick the size very wisely. The size cannot be too big, so it gets dropped, and when you reach all the routers, it can't be too small because you're wasting a lot of resources. Any questions about fragmentation? I'm pretty sure one of the final exam questions or multiple choice comes from what I just talked about. Big versus small IP fragments. So that's that. Just talk about it. Now, network layer functions. All right, this is a good time for a break. Let's take like 10 minutes break, and we're going to talk about the networks layer more.
We just said it's like
yeah, it's really no. So it's the IP or it's the IP and then it's